So we talked about, we're getting an introduction to electricity. Some of y'all already know this, so hopefully it was a review for y'all those. We talked about the best conductors of electricity. We talked about a little bit of physics, right? Talked about what voltage was, what current was, and what opposition or resistance was. We got to touch on something called reactance, which we'll get into a little more detail. We looked at series circuits, we looked at parallel circuits and series parallel circuits. We looked at some control devices, what we use to control the flow of current, and we said that how the control devices are hooked does not determine if it's a series circuit or a parallel circuit, right? You understand? What determines if it's series parallel or series parallel? How we connect the what? Load, right. We looked at some schematic symbols. We all don't have y'all's book yet, but told y'all where to go look for those and start learning them. Talked about line diagrams or ladder diagrams. These are what we're going to be dealing with a lot this semester. These guys are here. And you can see these are series parallel circuits. What's nice about it though is that our series circuits only got one load. So this is going to be a lot easier than what y'all learned in DC. Looked at different prints or different trades. Looked at commercial residential wiring, talked about schematics, talked about learning our symbols, right? Talked about voltage, amperes, resistance, and reactance, which we're going to touch on a little bit today because we're dealing with AC. And we're going to understand some of the things that we need to understand. We need to understand this thing called reactance.
The picture you showed earlier, the ladder diagram, it looked like the outputs were in series. Some of the outputs.
No, they're not in series.
Is that the circle? Is that
That's
an output right beside the contact?
I don't know what you mean. This is a contact. This is a load. This is a control device. This is not.
So you can put those in series.
Yeah, like I said, so here we got some control devices in series. Here we got some control devices in parallel. This control device is series, but the load, this is a series circuit.
Yeah. Because
the load, we got one load. Now what's nice about this is we're going to only deal with one series circuits, we're going to deal with one load. We never have, in line diagrams, we never have more than one series load. Never, never. We can have a lot of parallels, but we only have one series load. So all our series circuits are going to be one load circuits. Understand?
Yeah.
Yeah, this doesn't make it a series circuit. That's a contact. A contact is a control device.
It just made it seem like that would be an output.
It's not an output. It's a symbol for a contact, and we'll talk about that later on. Yeah, these are relays. These are coils for relays. These are loads. This is a symbol of what we call a solenoid, and we looked a little bit about solenoid. I did bring my nail in, by the way. So this is a solenoid. Let me bring my camera up. In fact, I need to. I forgot to do that. Logitech. I don't know why I can't get this to go full screen. I don't use this camera that much. Don't know what time the class starts, right? It's on your schedule. I can't get my camera to work, so it's okay.
Can't get what to work?
My camera to work. That's okay. Well, we'll just come up here and look at me. Looked at schematics. Let's see. Talked about Ohm's law and Watt's law, a little bit of that, right? Did some problems. Looked at the American wire gauge, and then we looked at ampacity ratings in free air, and then we looked at NEC ratings for conductors. And what NEC has done is took all considerations into it, and die rate means to decrease by a certain percentage, and they've die rated these, so you shouldn't have any problem in a residential or commercial installation using these, unless you go to, but if you look at National Electrical Code, it gives you some what we call die rating factors if you run through extenuating circumstances. And this is where we left off at. And this is probably one of the most misunderstood and misused term in the field of electricity, that and ground. So we're going to talk about a short in electricity. You don't mean a short in stacking. In electricity, what short means? Short is a what? Yeah, so when we have short circuits, we lose control of the current flow, which is not good. We still have current flow, but our control devices are no longer controlling it anymore. Shorts will always decrease the amount of opposition in a circuit, which will cause the total current in the circuit to increase. Y'all understand that? Always.
Shorter path.
And that's basically what it means. There's a shorter path to get back. Of course, the big one is this second one, a short circuit. So there's a difference between a short and a short circuit. And even though a lot of people misuse that term. A short circuit occurs when the source conductor and the return conductor come into contact with each other, which will bypass the resistance of the load. So if you have a short circuit, what's limiting the current in the circuit?
Just the wire.
And the internal resistance of the source. Y'all got to understand, a source has an internal resistance. So batteries have internal resistance. That's why when you go out and you put your meter on your battery and you turn your lights on, the voltage of the battery drops down because of the internal resistance of the source. Now, regulated power supplies, what happens if their voltage tries to drop down, it tries to raise it up, but it's only going to be over a certain limit, right? You understand? Once you exceed that limit, then you'll see the resistance of the source dropping all the voltage, not all the voltage, and we'll look at that in a minute. We got a deliberate short circuit over, I call it Big Bertha over here, but this big old DC power supply over here, we're going to show you all a short circuit. Short circuits are caused by incorrect splicing, incorrect termination, defective load, excessive current burning off the conductor's insulator, conductive items that fall into the circuit. So any of these happen, there's a good deal that we would have a short, but not necessarily a short circuit. All circuits must have resistance. If not, according to Ohm's law, the current and power will theoretically go to zero, infinity. So any number divided by zero is infinity, right? Most people don't understand that. And I usually tell y'all, get y'all's calculator out and divide any number by zero, and your calculator will come up and give you an error. Why can't your calculator give you an answer? Because your calculator cannot display infinity, right? You understand? In the old days in computers, computers originally could not divide. So we had to write programs to do that. And what you learn is that division is nothing but repetitive subtraction. And what it does is counts how many times you can subtract this number from that number without generating a borrow. Well, how many times can you subtract zero from any number and not generate a borrow? Okay, let's say 1 minus 0 is what? Okay, did that generate a borrow? Okay, 1 minus 0 is what? 1 minus 0. So how many times can you subtract 0 from an infinite number? Y'all understand? A lot of people don't understand what division is. Division is repetitive subtraction. And what we do is we start subtracting, and we can't, and then when we generate a borrow from the outside, then we count the number of times we were able to subtract the divisor, and that's what the dividend is, right? You understand that, or the quotient. So any number divided by 0 is infinity. If you got Siri on your phone, ask her what's 5 divided by 0. She gives you a lecture. So, but, okay, so I would go to infinity. If I goes to infinity, then the power would go to infinity. Of course, the current flow will never go to infinity because that's an impossible number to reach anyway. If the load is bypassed, the current flow in the circuit will be limited only by the what? And the internal resistance of the source. Y'all understand that? So all sources have an internal resistance. Regulated sources are pretty dangerous with shorts because they keep trying to they electronically raise the output up if it tries to do what? Tries to drop down. But even regulated power supplies has their limit. When all the loads in the circuit is bypassed, we call this a what? The current flows through resistance of the electrical conductor. Heat is generated when metals are heated, their resistance goes up. When resistance goes up, your power supplies start putting out more voltage because it's not having to provide all that current. But the big problem is resistance goes up, more heat is generated in the conductor. If something does not limit and stop the current flow in the circuit, the conductor will get extremely hot and may eventually do what? Melt the coil apart. So what usually happens first is the insulation is lost, and then after that, you have catastrophic failure. Two devices used to stop the current when the predefined level is exceeded. We call these what? Yeah. Any device that protects the circuit from a short is referred to as a overcurrent protection device, or OCPD. Not quite. So these are fuses. We got all types of fuses. Now, what advantages does a fuse have over the first one? Huh?
Cheaper.
Yeah, they're a lot cheaper per amp. So if you get out in industry, you're gonna see a lot of fuses. A lot of them.
But they're cheaper than equipment.
Yeah,
cheaper than equipment.
yeah. Yeah, it's scary. Yeah, you know, still that has a welding rod across the fuse, so something kept blowing fuses. So instead of trying to figure out what was wrong, they just
Make it to the shift.
make it through the shift. Make it to the downturn. That's what they said. Yeah, we learned that right off the bat. Rich, he says, you know, if we can get this thing to the downturn, he says, we would make all this much money. That thing might cost $5,000, but if we go down, we're going to lose $5,000 a minute, right?
And then that counts for the downturn.
Make it to the downturn. Yeah, then they work through the downturn. These are residential commercial circuit breakers. Now, of course, the big advantage of circuit breakers, they're more expensive, but they're not consumable, right? You understand? So normally what happens when we say pop, right? You understand, because they make that noise. You can do what? You can reset them. So that's the big advantage of circuit breakers, but they cost a lot more money. And they don't react as fast as fuses do. So this is a short right here. So notice we got a series parallel circuit, and this load right here is bypassed, right? I'll do that. So what would happen to the resistance? Well, the resistance is going to go down, and the current in the circuit is going to go up. Would this blow a fuse? Probably not. What you learn normally, especially in National Electrical Code, the circuit breakers or the fuses they choose is not in to protect the load. It's in there to protect that conductor. So it's in there for short circuits is what it is. So it's not in there for shorts. It's in there for short circuits. And this is why every once in a while you'll have an appliance that burns up in your hand, right, like a hairdryer, and your breaker don't even burp because it's still got resistance, right, and it's still not pulling the amount of wire to protect the wire. So most overcurrent protection devices are in there to protect against shorts, not what? Against short circuits, not shorts. Now, what would happen, though, is that according to Kirchhoff's voltage law, it says the sums of the voltage in a parallel circuit, in a series circuit, has to be equal to the applied voltage. So if we have to short, how much voltage does the short drop? No, it does not.
No, all of
It
it.
drops none.
To go to the other.
It's like coming in there and replacing it with a piece of wire. So what would happen if I've got 120 volts drop and these two had the same opposition? This guy would be dropping 60. Load 3 would be dropping 60. Load 4 would be dropping 60. Everything okay. When load 3 shorts, then load 4 is going to get 120 volts. And power would be V squared over R, right? Y'all understand that? So the power that thing consumes would go up by 4. Of course, that could cause all kinds of problems. So normally shorts cause other failures in the circuit. So that's a short. That would be a short. That would be a short. That would be a short circuit. Y'all see the difference? So here we've got something that's connecting the what? The source and the return together. Yep. To prevent short circuits, it is imperative that the conductors in the circuit are isolated from each other. The substance that isolates the conductors is called a what? Insulator. Insulators are made from substances that exhibits an extremely high opposition to the flow current. There's nothing that has infinite opposition. You don't understand that? Yeah. If you take cable splicing insulation, you learn that there's even current flow through the insulator because you have a path and you've got a resistor in the center of it, right? It's just that the current flow is so small that and it holds the push down. The insulator doesn't hardly drop any voltage, right? You understand that? So it basically, to us, the insulator doesn't do anything. Just holds the push in, right? An open allows no current to flow through the load. If no current flows through the load, no work is done because power is equal to I squared R, right? You understand that? So this is the one. Most people call if they've got problems in a circuit, the average person calls them what? Short. I got a short. We got a short in it. Like I told you, my mom called it a shortage. You know, if you get out there and you go to work for somebody and they call it that, you let it go. But if you got people working under you, they need to know the difference between a short and an open. So most of the things people's calling a short is actually a what? An open. Now opens are pretty neat in that open circuits prevent current flow through the entire circuit. Open circuits. An open, we're talking about one load, right? You understand? An open circuit, we're talking about an entire circuit. So a circuit breaker creates an open circuit. So if you go back there and your circuit breaker kicks, what happens to everything on that branch? Well, everything goes off because you killed the current flow in the circuit, right? You understand that? Of course, we deliberately create open circuits all the time. I don't know of anybody that's deliberately, well, I do too, I'm not going to say create shorts. Normally we don't, but we create open circuits all the time. With what? For switches, yeah. So I've created an open circuit right here. This is a closed circuit. This is an open circuit. Now, when you take hydraulics and pneumatics, it's just opposite. Anybody taking that? Anybody taking fluid power yet? But here they're talking about fluid. So us and fluid power are opposite. Fuses or circuit breakers, faulty splices, faulty termination, or excess of heat that causes the conductor to block. Melt. So this would be an example of an open. This would be an example of an open, right? That would be an example of an open. That would be a what? Open circuit. We've disconnected the source. This would be a what? Open circuit. And people have problems with this. Well, a circuit breaker basically would be used like this guy right here. But a circuit breaker is a device that automatically creates an open circuit if you exceed the current, right?
What I was asking, in that circuit where you showed the open circuit, that's where you would normally put your circuit breaker.
Yeah, what we do is we put so here's, of course this is a series circuit, but here's a symbol of a fuse. So what do? We put the fuse so it creates an open circuit. Okay, y'all understand that? Now what we have here, this is a little program we have called electronic workbench, which is pretty neat. It's a simulation circuit. So what you do is you draw the schematic of your circuit, and then it actually simulates the real part, the real circuit. So right now we have no problem. So what I've got it set up for is that I can come up and what can I do with the parts? I can short them. I can do what? I can open them. So right now we'll start off with none. And we'll turn the circuit on. And this is an ammeter, so right now it's conducted, the whole circuit is conducted what? Yeah, about 1.9 milliamps. And back in DC, when you get into DC, you'll learn how to calculate all this. What we're going to do now is we're going to, so 1.846 milliamps. We'll come up here and we'll short this guy right here. Okay. And we turned it on, so what just happened? Current increase. Now these guys up here are got to make up the difference, right? You understand? So this is a voltmeter right here. Let me, this is a simulated voltmeter. Let me find the actual meter. Then what we're going to do is we're going to come over here and we're going to put the meter across this resistor right there. What's it going to measure? How many volts is it going to drop?
On the open?
No, that we're dealing with shorts right now.
They're gonna read that.
Yeah, it's going to read pretty dang close to nothing, right? Y'all understand that? We'll see if it does. So we'll come up here and we'll turn it on. If it was on. 0.0022 microamps, or it's reading, that's microamps, right? So that's the best simulation you can do.
Microvolts.
I'm sorry, microvolts. Because we're reading both. So when you got a short circuit, this is one way you can find it. You can measure the what? The voltage drops across there. A short will drop no volts. So how many volts should a fuse drop? Well, I'm saying a fuse. Now, fuses are not, fuses, we don't use the term open or closed. We use yeah. So a good fuse, how many volts should be across a good fuse? A fuse is going to drop a little bit of voltage because it's got to have resistance, but it's got almost no resistance. Because if it didn't have resistance, it would never melt, right? You understand that? Yeah, so it's got a little bit of resistance. So it's dropping right now 218.2 microvolts, which is basically nothing. So how many volts should a closed switch drop? Probably it's going to drop less because it should have no resistance in it. Okay. So see, this guy here drops how many volts? Yeah, 0. Now what's going to happen if I open the switch? Yeah, we read the total voltage, right? Which is 12 volts. It takes a little while for the to update. By the way, it's minus because I got my lead swapped around. That's okay. So an open element in a series circuit is going to drop the applied voltage, right? You understand that? We come up here and close the switch. Notice the voltage drop across the switch drops down to 0 because it has no resistance. So even though it's conducting this current right here, if you take this and multiply it by 0, so V is equal to I times R, right? And how much resistance does the good switch have when it's closed? When it's closed? 0. Yeah, 0. It's got none, right? You understand? So if you take 2.2 milliamps and multiply it by 0, then the voltage drop is going to be 0. This is a lot of people hurt. So right now, if I went back to these outlets, these switches back here, and I measured across the switch that's controlling these lights right here, what would it measure? It's gonna measure 0. What would this switch measure? 120 volts, or whatever we have. So let's go over and short this guy. So let's turn this off. And what should we expect to happen? Current better, yeah, current's going to increase. Yeah, R3, so R3 is going to be doing a lot of work, and that's what happens because you have a short over here. The other ones have got to make up the work, right? You understand? Now what's going to happen when I short this one? No.
No, the other two. Yeah. The other two. You basically got a short circuit.
No, I didn't show it, but what happened? Yeah, the fuse blew. And of course, to check a fuse, normally what we do is we come over here, we're going to measure across it, right? And if it measures the applied voltage, then that means it's what? Yeah, but it's not doing that.
You put an open.
Huh? Oh, I did?
Yeah.
Oh, thank you. This will blow the fuse. Okay. See it blow? And of course, what's across the fuse? The source of it. That's what we have up there. We're using the 12 volt supply right there.
Does that say minus 12?
He got his lead swapped around.
I can't see that.
It does say minus 12 volts because I have my black lead. I have my black lead toward the positive and my red lead toward the negative.
So it's still 12 volts.
It's still 12 volts. That's the important thing for y'all to. In the old days, we were really concerned about when we had analog meters because they were pointer meters. So if you didn't put your leads in there right, the pointer would peg up against the minus, and it could cause the meter to be in, the actual pointer to be. Digital meters, we're not really concerned. So that black lead is not a circuit common. The black lead is a common to the meter, right? You understand that? So in a DC circuit, if you hook them up backwards, you just get the opposite voltage you get the opposite polarity from what you expect.
That's on digital.
On digital. Now digital,
Very important.
very important. You can mess up your pointer. Then you bend that little pointer and it's so fine anyway. If y'all have ever seen one, it's a really narrow thing. And then they put an end stop and it'll peg up against that. If it's up here, it'll peg up against that. If it bends that, then all your readings would be off after that.
No, if it's dead giveaway, you got something wrong.
Okay. So we have to put a new fuse in there, by the way, it won't work. You gotta storage it. Well, it's harder with analog. A lot of your newer digital meters are putting an analog scale on there. So the better meters, so you can actually see it do that kind of stuff. So let's come up here. Let's take out our shorts. Now we got a fuse replaced. These are still red, so I didn't do anything. Okay.
You put open on the open one.
I did again. None. Okay.
The other one. Or
Okay. So we'll fire it up again. We should go back to the first current we were at. We measured, right? So what would happen if R1 opens?
If it open, it's
current.
all your voltage is dropped right there. If it's open.
Yeah, but what happens to the current in the circuit? Yeah, the path stops, right? So we turn it back on, our current goes to 0. Okay. So what voltage drop would I measure across R2?
With an open circuit.
Why?
Because all your voltage is dropped across that open.
Why?
It's got
it's got infinite resistance, but why in this guy right here dropping?
Because the current.
There's no current. That's the point. Yeah, to get voltage drop, V is equal to I times R. If you have no I, you have no V, right? You understand that? So basically what that's doing, if this guy drops no voltage, that's going to take this common and put it right there. It's going to take that common and put it right there electrically, right? Your power comes up here, and that's why you measure the full voltage across the open. Because nothing else in the circuit is dropping any voltage. If nothing else in the circuit drops any voltage, then all the voltage is going to be across the open. So we're not getting voltage drop because of I times R. We're getting voltage drop across the open because nothing else in the circuit is dropping a voltage. Yeah, so you got zero. So if this guy this simulation is off a little bit, but that's microamps. So that would be nanoamps. 6.6 nanovolts, yeah. So the simulation is doing the best it can do. It did a real good job with the switch. So if I open up any resistor in this series string, then what happens is all the other guys don't do the work. So that's why, you got your Christmas tree lights and you lose one, what happens? That whole string goes out. In the old days, you had a series circuit. But now you have series parallel circuits. Most of your lights are series parallel, so you lose a section of light, but the other lights work okay. So let's go down here and look at this guy. This is what we call a parallel circuit. So let me take the air out of this guy. Yeah, I pulled it off. That's okay. Don't take long to get back up. Now this is a parallel circuit. And this is the way your house is wired. Your house is wired parallel. So what's going to happen if, so we'll look at the current. Let's fire this up. So right now we've got 21.1 milliamps. We've got 12 volts applied. Fuse is okay. So what's going to happen if I short any of these guys?
What's going to happen to what? Current or the voltage?
Well, we know the current is going to go up, right? Now we got to figure, okay, is it a short or is it a short circuit? Well, in parallel circuits, it is a short circuit. Because as soon as I short, here's my source conductor, here's my return conductor. Y'all realize that we're using this as a symbol to represent a wire. So this is when we start changing. Y'all understand that wire is there. But the more we can replace with a symbol, the less complex or crowded the circuit becomes, right? You understand that? This happens all the time when I start teaching like DC. They'll say, well, this is inside the trainer. And I say, of course not. So they'll wire the circuit up. They'll have these resistors down here. They'll have nothing down on the bottom. But this is the symbol for a wire. Y'all understand that? So you got to put that wire in there. So what happens is this is my return conductor. This is my source conductor. If this shorts right here, then that's going to do what? Short circuit. So parallel circuits, every short is a short circuit. Series circuits, every short is not a short circuit, but every open is an open circuit, right? You understand? And what you'll learn while you're in, you'll learn that parallel circuits and series circuits are just opposite of each other. So if I come out here and shorted R1 in my series circuit, that was not a short. That was not a short circuit. That was a what? That was a short. So the only way I got a short circuit is to bypass all the loads. But I opened up R1, that was an open circuit. If I open up R2, that's an open circuit. If I open up R3, that's an open circuit. So in a series circuit, every open is a what? It's an open circuit. But every short is not a short circuit. But over here, we come over here, still got power on. Let's come up here and short this guy out. Now, as soon as I do this and turn it back on, what we expect to see? Well, we expect the fuse blow. Because that's a short circuit, right? I just did what? I just connected my source and my return together. So let's take out this. And it shows it okay, but it's not. But here's my fuse. Okay, so let's fire it back up. So we've got 21.1 milliamps again. What should we expect to happen if I open up R1?
All you, turn the voltage go through the other.
Well, the voltage, if we look at a parallel circuit, so in a series circuit, the current is the same through the circuit. Now what's distributed in a series circuit is the voltage drops. So if I go up here and it's relative to the size of the resistor. So the biggest resistor drops the most voltage. And when you get into DC, you'll learn how to calculate all this. But see, I'm gonna come over here. This is 3.3K, and it just works out better, by the way, for me to put the negative on that side. So I'm gonna turn it on. This guy right here is dropping about 6.1 volts, right? You understand that? Then I'm gonna come over here and move my meter lead over here. This guy's going to drop less because it has less resistance. So it's dropping about 4.1 volts. And then I'm going to come over here to 1K. It's going to drop less because it's the same thing. I mean, because it's the smallest resistor. Now, if I was to add all these voltages up, I would come up and get 12 volts. But the current in the circuit, the current has only got one path. So this is in series, so everything that's flowing has to go through that. So it means I have 1.846 milliamps flow here, I have 8.46 through there, I have 8.46 through there, I have 1.846 there, I have 1.846 there, I have 1.846 here, right anywhere in the circuit. So if you want to measure the current in the series circuit, where can you put your ammeter? You can put it anywhere, because there's only one path. So what's constant in a series circuit is current. Well, when I come back here and look at my parallel circuit, I notice that the top and the bottom of every lead is connected to the source. So if I follow this right here, it connects to the source. I follow this right here, it connects to the source. So if I come over here and put power on this and measure across any resistor, what's it going to measure? Well, it's going to measure 12 ohms. So this is why you can go to any plug in your house and put your meter in that and put it on AC, and it's going to measure whatever yours measuring. We say 120 volts because that's NEC calls the optimal voltage. But what does this measure? 12 volts. So in a parallel circuit, what's constant? Well, voltage is constant. Thank goodness. Wouldn't that be awful? You know, in your house, if you plugged in your vacuum cleaner and now your oven couldn't work because it wasn't getting enough current, right? You understand? Because the voltage would be distributed out. But we have a problem with a parallel circuit in that every short is a what? Is a short circuit. But I can come up here and open this. What's going to happen? Well, it's still going to, total current is going to go down. Right? You understand? But the voltage is still 12 volts because it's an open. So opens in a parallel circuit is a little harder to find because if it's open, it's going to measure source voltage, right? You understand? If it's working, it's going to measure source voltage. So it makes it a little harder to find opens unless you measure the current in that range. But notice total current went down. So this is why when you go out there and you turn you turn things off, if total current goes down, then total power consumption goes down, right? You understand that? So this is why you tell people to unplug stuff and turn stuff off because, because if you leave stuff on, then it's gonna create another current path, right? You understand that? Yes or no? Yeah. So if we open this guy, this is an open. This is not an open circuit. This is an open. So notice what happened. Total current went what? Went down. Because now we're not supporting this current through here. So here, this guy right here would conduct the most current because it has the smallest resistance, right? this guy would be here. So what happens every time you undo the load, total resistance goes up and total current goes down in a parallel circuit, just opposite of a series circuit. Series circuits and parallel circuits are just opposite of each other. But your house is wired in parallel. So this is why we can do what? We can plug stuff in. When we're through with it, what can we do? Unplug it, right? And when I unplug it, it don't consume any power, so that power is not added to your power bill, right? You understand that? So on a parallel circuit, every short is a short circuit, and every open is not necessary. How would I get an open? Well, I could come up. How would I get an open circuit? Yeah, we got to open something in the branch, so I could come up here and we could come up here and do this. Okay, now I have a what? Open circuit, because now all my loads are past my open. I come up here and turn this on, my ammeter comes up and should go. I don't know why it's saying error. I guess because it's not connected. Oh, we got a problem out here. No, the simulation is not working right. Let's open it up over here. So electronic workbench is telling me that my circuit is not complete. See what would happen if we open it right here. Well, we could open it with the switch. Yeah, but I think it's going to give us an error. We'll see. It's not giving me a, oh, there it is. Let's open it right there. So total current in the circuit with the what? So to get an open circuit, and this is why we put our fuses or our circuit breakers right here. We put them in series, right? You understand? It's not a series circuit, it's a parallel circuit. But when we connect something in series, it means we connect them in line. So if my fuse right here blows, it creates an open circuit. Any questions on that? I don't have a slice ID. It's not going to have this in there. They don't have electronic workbench in there. If that's what you was asking. No, this application, it's not called electronic workbench anymore. It's called, I can't remember what it's called. And so this is a pretty old version. It only runs on Windows XP. So I'm actually remoted into another computer in my room over there. Okay, guys, y'all take a... Same book.
I'll tell you when it's gonna be here, when you go down there. I have been talking to Mr. All the lady.
Okay. Okay, guys, let's get into AC and DC. And so we're going to touch on this. We got to know some things for this class because we're dealing with a lot of AC. All our controls are AC. So what's direct current? Yeah, it never changes polarity. So the source never changes polarity, right? You understand that? And what's the advantage of DC? Yeah, we can control DC precisely. So that's why my cell phone is DC, your stereos are DC, your TV is DC, even though you plug it into a wall outlet, there's a thing called a power supply in there that turns the AC into DC. These are produced by DC generators. They're produced by batteries, which a lot of y'all produced by things called thermocouples, which use heat. Solar cells, y'all seen a lot of these. These things produce DC from light. Piezoelectric devices, these are devices that when you shock them, they create a DC voltage. Any of y'all guys that smoke or got the clickers that you pop, that's a piezoelectric lighter that you're using. Electronically, power supplies. So when I look at my computer runs off of DC, but I plug it into Alabama Power, so what do I have? I have an AC to DC converter right here, right? You understand? Or a power supply. In bioelectric, we are bioelectric. We create DC. That's what we run off of. We run off DC. Well, that's not true. We run off blood, but we're controlled by DC. So our brain processes DC pulses. So we're bioelectric. If you ever watch the Matrix, I don't know what they use this as batteries. We were batteries. So here's some devices, DC generators, batteries, y'all you real familiar with, solar cells, piezoelectric, and a thermocouple. Thermocouples we use, these are really accurate to measure temperature. And I don't have a DC power supply up here, even though I should, because they're used all over the place.
Rich, on your films, on your classes, you get full-size screen.
What you need to do is, not in Blackboard, but you can go to YouTube and just search up for my name, Rich Raymond, and you'll be able to watch it. But if you go up there, you're going to have to find the lectures, because they're all up there. But it's going to be ETC, it's going to be ETC 108. All the ones that deal with this class is going to be ETC 108. So that's what I do when I upload them. I started off with that. And that way you can watch them full screen if you want to. Alternating current does what?
Constantly swaps.
Yeah. The voltage source is AC constantly swaps polarities, which causes the current to do what? Change directions. So AC has no polarity. So people get tied up on their meters and they think you got to put the black lead on the neutral and the red lead on the hot. That's not true in AC. It makes no difference. Yeah, AC has no sign. If you could put it in DC and you put your digital meter in there wrong, it's just going to show you the wrong sign. But AC has no sign, right? You understand that? The big advantages is what? Less expensive generation. We make AC really, really easy. Extremely efficient to transmit over great distance. Transmit power. We can easily change the voltages with devices called transformers. And AC motors are less expensive per horsepower, but they're harder to control. These are produced by what? AC generators are produced electronically. They're produced bioelectric. So there's an there's an AC generator that we have on our cars that we call alternators. And some people have the mobile AC generator. We had the 13 inches of snow in '93. Moved out of power. We were lucky. We was out of power about 4 days. So I went out and bought me a generator. How many times have I used it since then? That's what I do power. Power plants generate AC. Electric field generates AC. Electric field generates both AC and DC. DC to AC converters, inverters, some of y'all have that, and then these things called function generators, which I have up here on my car. So that's electronic. Now what happens? We're dealing with power. Well, we have different forms of AC, but what we're dealing with AC power. So what happens is the AC is constantly reproducing itself. And we'll look at that. AC waveforms is referred to as a sine wave because the voltage varies with the trigonometric sine of the voltage, current, and power, which makes no difference in this class, but it's a nice, pretty wave. So we'll come up here. This is AC being generated. So AC is generated on a circle. And what we do is if we can take the sine of theta, which is this angle here, y'all see this is forming an angle, right? See that? And if I was to drop the sine of theta where it's at, and then I multiply it times this big voltage, that would tell me what voltage that would be anywhere on the sine wave. And so that's why we call it a sine wave, because it varies with the sine of the angle being generated. But notice how smooth it is. And this is a sine wave. If I was to take an oscilloscope and look at Alabama Power, I wouldn't see it moving like this. Now this is where we got to learn terms. So we're showing two complete alternate, two incomplete. What do we call this? One complete. So we have a positive voltage. We have a negative voltage. These two guys are mirror images of each other. And these guys are constantly repeating. They constantly repeat. The only time they stop is when you turn the power off. So we have what we call a repetitive waveform. So if I took this one and put it on top of that one, they would lay right on top of each other. They were identical to each other. Everybody okay? So we call this an alternation, by the way, for obvious reasons. So we have a positive alternation, we have a negative alternation, and then we hit this point right here, and it all starts it over again. And we talk about what we call, and notice it's generated on a circle, and a circle has degrees, right, to understand. So when this thing makes a sweep of 360 degrees, it generates one cycle, or one waveform. So we talk about degrees. So this would be 0 degrees. What would this be right here? 180. This would be 360 of this one, but it would be 0 of the next one. What we use, we talk about midnight. What is midnight? It's the end of one day, but also the start of another. Y'all understand that? And we call this one repetition of this repetitive waveform, we call it a cycle. Everybody okay? And these cycles are occurring at a certain rate. So a cycle is what? One repetition of a sine wave, 360 electric degrees. An alternation is each half of cycle. But that thing next, this is called what? Frequency. What is frequency? The rate of the sine wave. And it's measured in cycles per second. Anybody know what Alabama Power? Some of y'all should know that. What is Alabama Power frequency? 60 cycles per second. But most of the time, it's just like in most sciences, is that people who are fundamental in the developing of the science have the privilege of getting their name, like Ohms, right? You understand that? So I don't remember what Hertz's first name was, but he was honored with the cycles per second being indicated by his name. So Hertz stands for what? Cycles. So Alabama Power, we say 60 Hertz. So this is what Alabama Power generates. So it needs one cycle. So if it's 60 Hertz, how long? So that's cycles per second. So how long would one cycle be? Nobody got any ideas, guys? 1 over? Oh, 1 over frequency. Well, that's true. It's going to be, so that would take 1/60th of a second. And this would be 1/60th of a second, right? 60 cycles per second. Now, if we did the math, this would come up and be 16.666666 milliseconds. And that would be what we call the period. So the period is a what? Time it takes per cycle. Now, we're not going to be dealing with that. We're going over to Europe. We're going over to Germany. And anybody know their frequency rate over there? 50 Hertz. 50 Hertz, yeah. They do 50 Hertz. They don't have a thing. They don't have dual voltages like we do in our houses. Theirs is 230 volts. Period.
How much?
230.
What do they sell? Converters for you guys to use? So.
Yeah, they sell converters. They sell adapters. Most of your electronic devices now, if you look at the power, the voltage rate of it, most everything now is dual voltage. So if I look at this power supply right here, it says it can run on any voltage. The input voltage can be any voltage between 100 volts and 240 volts.
Unplug the other plug and have another.
Yeah, but their plug is their plug is two round rods sticking out. If you look at it from the front, it looks like that. So you can have an adapter, but if you got something that don't run off that, then you do what you buy what they call a converter. Yeah, but I'd have no problem with this. The only thing I got to do is get an adapter to adapt it over to the European plug, right? Now my electric toothbrush is rechargeable. It's only rated for 120 volts. So what, I have to charge my toothbrush? Yeah, I charge up 20.
You may have to go with mine.
You might have to use your hand.
No, I bought me a converter. It was only like 24 bucks.
Now, when you plug those computers in, you better be careful.
No, that's no big deal. That computer right there is 240. That guy right there, they got no problem. So most of your little bricks, the little bricks that charge your cell phones and stuff, look at there. They're usually rated at what? 110 to 240 volts. So all you'd have to do is just adapt over to the. So this is not really important for this time, but so time is 1 over frequency, and frequency is 1 over time. But we do need to understand hertz, because hertz becomes important later on when we start talking about speed and phase shifts and stuff like that. We have what we call three-phase power. So y'all understand degrees now, right? So degrees is, so one cycle would be equal to what? 360 degrees. So 120 degrees, so this would be 90. So 120 would be right in here somewhere, right? You understand? So what we do with three-phase is they generate the phases 123 electrical degrees away from each other. Now the advantage of three-phase is more efficient to transmit, but it requires 3 conductors. And if they ran three-phase to your house, it would take, instead of having 1 transformer up there, they would need what? 3 of them. Very expensive to run. But if you're going to send stuff long distance, or if you have an extremely high power demand, then odds are you're going to have 3-phase. If you don't have an extremely high power demand, like my house, then it's going to be what we call single phase. It depends on how you run them. We'll talk a little bit about that later on. We can run a delta, what they call a delta connection, which requires 3 conductors. If we run what we call a Y connection, which we might have 4. These are used for power transmission over long distances. It's used for 3-phase induction motors, 3-phase power motors, and 3-phase motor drives. So you don't have 3-phase in your house, but y'all probably seen it before. So this is the way 3-phase would be generated. We basically have a generator that has these coils that are placed 120 electrical degrees apart, and then so we have 3-phase there. We have 2-way 3-phase, and the motors that we're going to run are 3-phase motors. So we need to understand some things about this. And the big advantage of a 3-phase motor is more efficient than a single-phase motor. Here's 3-phase. This is power transmission. Can y'all see the 3 lines? So here's 1, 2, 3. It's really neat. We'll talk a little bit later why 3-phase is more efficient, because the load is shared between the 3 lines, 120 electrical degrees apart. Power and AC. Basically, our formulas are the same, but this is the thing right here. This is power. So the primary formula for power is what? P is equal to what? Now the next one is what's so important. This is what makes AC efficient to transmit. Is the amount of current that's required to produce that power would be equal to P over P. You understand that? We okay? When current flows through resistance of conductors, the current produces voltage drops. The higher the voltage pushing the current, the less current is required to provide the power. What's Alabama Power selling you? Power. Okay, y'all understand that? Transformers step up or step down the AC voltages. We step it up for transmission, we step it down for loss. So transformers do not change the power required by the load. So theoretically, I come up my house and I turn on a 100-watt light bulb, then whoever's giving me power supplies me 100 watts. Right? Now, if the transformers were 100% efficient, that would be true. They're not. But their transformers now are well over 90% efficient. They do have a little bit of core loss. If they didn't have core loss, they wouldn't get hot. So what that means, if I'm trying to provide power, I think we looked at this the other day. So let's say I'm trying to provide 1,000 watts. 1,000 watts at 10 volts. What would my current be? Huh? It would be 100 amps. Let's say I'm trying to provide that same 1,000 watts at 1,000 volts. 1 amp. So what does this mean? Well, that means when I run that current through that conductor, that conductor is not going to drop as much voltage, right? You understand that? But 1,000 volts would be very dangerous, right? You understand that? 10 volts wouldn't be. 10 volts is below the legal limit. But when we buy things, things are rated in two things. They're either rated in a voltage and a current. Now, resistors are not. We're talking about appliances. So if you look at appliance and you start looking at the tags, it's going to tell you what voltage it's designed to run at, and it's going to tell you what current it is. If you change the voltage, if you raise the voltage, what's going to happen? It's going to burn up. Because the load is what requires the power. It's just what we're talking about is how do I get that power to the load? So if I got a device that's designed around 120 volts, then by George, I better give it what? 120 volts. But I can come over here and I can have a transformer out there on my pole that has 120 volts. But on the primary side over here, I can have 1,000 volts. Now over here, I'll have more current to produce that power. Over here, I have less current, right? You understand, to produce that power. So I know in Ohm's law, we say, okay, if voltage goes up, current goes up, but we're not talking about the load. We're talking about how do we get the source to the load, right? You understand that? So these are some three-phase transformers. This is probably one of the most popular. These would be a three-phase transformer. Now, the problem with this, if you lose one of your transformers, you have to replace the other transformer. Most of the time, you'll see these people that run three-phase don't actually have three single-phase transformers. And that way, if a transformer goes out, then they can just place one transformer, right? That makes sense. And these substations, these are nothing but transformers. So this is just an analogy right here. So here's my house. We have two voltages, 120 and 240. Of course, y'all are going to vary. Okay, and what I'm doing is over here, I'm going to turn on a load that's designed to run at 120 volts. 1,000 watts, 120 volts. What does my house need? It needs 8.3 amps. Okay, that makes sense. And what would be the wattages? It would be 1,000 watts. So if I have 1,000 watts on this side of the transformer, what watts would I have on this side of the transformer? 1,000 watts. I'm not changing work, right? You understand? Transformers don't change work. A 100-watt bulb is a 100-watt bulb. How much power do you have to give? You have to give 100 watts worth of power. But what happens over here on the 2300 side, what happens? Well, now all of a sudden, now I'm giving it at 2300 volts, and what's my current? 435 milliamps. Which means what? I can use smaller what? Wire. I can use smaller wire. Or I can go to a different type of metal besides copper. Right? You understand that? So transformers do not change power. They just change the voltage that power is delivered at. So people say transformers vary voltage, but if they vary voltage, they're also going to vary the current because they don't change the what? The power. Okay, now we come over here to these things we call substations. Now over here I'm delivering it at 275,000 volts. So now I'm down to what? 2.6 milliamps for my house. So these are these big old substations. What do they do? All these big things we call substations. They're either doing what? Stepping up for transmission or stepping it down as soon as we start getting close to ground, right? You understand that? Then I get back to my power company. Now my power company is generating at 2200 volts, which is pretty standard. Now, it depends on how they got what they call intrastate, interstate. Depends on how far the power runs, depends what voltage. They get up to over 700, I think it's 725,000 volts on some long distance transmissions. But what they can do here, instead of using copper wire, they can go back to what? Aluminum. Because even though aluminum has higher resistance, the voltage is so high, the current drops down so low that they won't have a lot of line loss. Normally when they get into here, guys, this is usually copper. Except a lot of times your down drop will be aluminum because it's so. Now this is the only one insulated right here. These right here are not going to be insulated. And why? Well, it adds a lot of weight to the conductor, but it also adds resistance to the conductor, right? Because now the conductor will get hot. So that's why we change voltage. Change it for what we. So which one over here? If I had a device designed around 240, or if I had a device around 120, the 240 would require less current, right? You understand that for that power. So all your high wattage devices are designed to run on what? 240. Are they going to say, is that going to save you money? No, because you're not paying for 240, you're paying for power, right? You understand? What it does is when they run it, they can run smaller conductors. So now I can run those conductors through the wall instead of running them under the house, right? You understand that? And it's going to be cheaper to install, but it's not more efficient to run. And a lot of people get that. A lot of people think that. Because you do that. But if I took my air conditioner and tried to run it off 120, it's probably going to not even run, right? You understand that? If I tried to take something designed around 120 and run it on 240, it's going to burn it up as soon as I plug it in. So your loads are designed around a certain voltage. And you need to run it on that voltage, right? You understand? So 240 means smaller conductors. So you get some of these big companies, they're running these big old high horsepower motors. They're going to run them on high voltage. They're going to be, the motors are going to be designed around a high voltage. Because now they can run smaller conductors out there, right? Y'all okay? So we have 208 and we have 120. We're going to use 120 for our control voltage and we're going to use 208 for our power voltage. So that motor right there is a dual voltage motor, and we'll talk about later on. And this is something people don't understand too. The instantaneous voltage of an AC sine wave constantly changes. The DC average of a complete cycle is equal to what? Yeah, so what I'm going to do, a lot of people don't understand this. Let's see if I can get this over here. So I'm going to take my meter, I'm going to put it on AC, put it on volts, 200 volts. I'm going to turn it on, and I'm going to put it into this outlet over here. And I'll put my camera up here so y'all can see it. I'm going to try. Oh, don't see it. My camera's not, I can't get my camera to go full screen for some reason, but it is working. Let me check my meter before. Oh, okay, thanks. Duh. That's what I was gonna demonstrate. Okay. So what's it measuring? Okay, so that's what we have here, single phase. Now what I'm gonna do is I'm gonna come over here and put, so we got this button right here that switches us between what? Okay. Yeah, but what I'm trying to show you is the average value of the DC average of a sine wave.
Positive and negative.
Cancel each other out. So here's AC, and this gets a lot of people work. These meters you got to be really careful about because you got to remember to switch it from what. And when I turn it off, and then I turn it back on, okay, it went to AC. Okay. It went to DC. So what's the DC average of a sine wave? 0. So if your meter's not set up right and you got it on DC and you go in and measure AC circuit, it's going to measure 0 and you're going to say there's nothing there, right? You understand? So you need to be real careful on that. So that means when we figure out, but what we had to do, or what they had to do, I had nothing to do with it. They had to come up with a method of calculating a voltage where the negative and positives, when we start talking about work, the negative and positives do not cancel each other out. Everybody okay? So they came up with a method called the DC average of a cycle is 0. Proved it with my meter, right? So a method of finding what we call the effective voltage, nobody should call this an average voltage, just an effective voltage, is to take the square root of the mean, which is the average, of an infinite number of equally spaced instantaneous voltages along the sine wave, and then sine wave squared. We call this RMS, or the root of the means of the squares. Now, what's neat is that if it's a sine wave, then it will always equal to the positive peak voltage times what? 177. Reciprocal square root of 2. Now, most AC meters measure RMS by using this value right here. And it works great for sine waves. Don't understand that? Yes or no? If it's not a sine wave, you don't have a meter that has the ability to do that, then it's not going to measure the correct value. So we have another type of meter that costs considerably more. But odds are you don't need this meter unless you work on variable frequency drives and that kind of stuff. You know, see what this is? True RMS. So this is a true RMS meter. So this guy has got a microprocessor in it or a processor unit that actually calculates RMS. So this would give you the effective voltage no matter what type of AC you get into. But that would probably be about 5% of the people in this class that need this meter. Y'all understand? Or less. Odds are you're never going to run into a situation where you're going to need a true RMS meter. That's up to you to decide. But we do have variable speed driving here that chops the voltage up. And what would happen, we can measure the voltage with this, but it wouldn't give us the true effective voltage that I'm seeing. So any type of things like that, variable speed drives, pulse width modulation, and that kind of stuff, if you get into those, if you're going to be dealing with those electronic circuits, then odds are you need to get a what? Yeah, true RMS meter.
Huh? So what you're saying is, if you took that meter Hooked it up where you can get to zero, you could,
No, it's gonna measure zero. The average value of us, the average value,
it's gonna measure zero.
they're gonna measure zero. If I put AC on there, it's gonna measure 121 volts, because that is a sine wave. So both these meters are gonna measure exactly the same thing. Well, I'm not, maybe not, but they're gonna be close.
Yeah.
Okay. I don't know what this one is. I think this might be a 6,000 count meter. No, this is a 400 count meter. This is what we call a 200 count, a 2,000 count meter. So this one would probably might show it a little, but it's still going to be so close you wouldn't be able to tell the difference. Yeah, the only time it comes into play, is that if you're dealing with non-sine wave signals. If you're dealing with nothing but sine waves, then you don't need a true RMS meter. So a lot of people have a true RMS meter because they can say, I got a true RMS meter. You know, it's just like a lot of people buy these cell phones and never use the feature that's on there, but they can brag about it. There's very few people that use every feature that's available on their cell phone. And a lot of them don't even know they're there. Like mine's got Siri on it. How often do I talk to that lady? Yeah. Except I did say what's 0 divided by 0. Because somebody told me about that. And it's something like if you have 0 friends and 0 something like that. So if you got her, y'all need to ask her that. What's 0 divided by 0? What would be the RMS value of a, this is about, by the way, this is Alabama Power. Alabama Power has 170 volts peak, about 340 volts peak to peak. So what I would do is I would take that 170 volts and multiply it by what? Yeah, and it comes up to be, so there's your 120 volts right there. So this is peak voltage. What you have to understand is that the voltage actually looks like this. What we do is we take the value of that peak voltage, and this is what we multiply by 0.707. We have something called peak-to-peak voltage, which would be twice a peak, right? You understand? So Alabama Power is actually sending out about 340 volts peak-to-peak to get that 120 volts, which to us it seems like to be, you know, a waste of voltage, but it don't make any difference because they can step this stuff up and down and get whatever they want, right? You understand that? And plus, we have the ability to send these things to transformers. And what does transformers do? The voltage, but most people just say that, but they don't understand if it steps up the voltage, the current goes down. If it steps down the voltage, the current goes up in the transformer because it don't change the power, right? Now, don't get this confused with Ohm's law because Ohm's law is telling you what happens with the load. So if you raise the voltage on a load, the current's going to go up if you raise the voltage, but it's going to produce more power. What we're doing is we're talking about the source. What goes on with the source, right? Y'all understand? Not the load, the source. So that means if I've got this 120 volts right there, and this is producing so much power, you know, like we said, 1,000 volts, and then I move it over here, and then I do what? Then I have that 1,000 watts over here, but this is going to be at a different voltage, which means the current is going to go down, but it's still delivering 1,000 watts to the load at a voltage, right? That's required by the load. Yeah, if you change the voltage on a load, then the load is going to respond according to Ohm's law. But we're talking about the source. The source. How do we get the power from the generators to our load? Everybody okay with resistance? So we're adding a little more definition to this. It says opposition to current flow that does not change with what? Frequency. All opposition in a DC circuit is resistance. There goes mine. $280.
You were talking about it anyway.
If that'll hurt it,
Okay.
then I would be very concerned. Yeah, most of our test equipment is built really, really well. Huh?
I would like it to last that much longer.
Yeah, and that, unfortunately, Carcam bought that for us. Unlike resistance, reactance varies with frequency. In a device called capacitors, as the frequency goes up, the opposition does what? Goes down. In devices called inductors, as frequency goes up, opposition goes up. But it's still in ohms. But what happens here is we got devices where the opposition actually changes. But this only works in AC. Okay, where's my... Here. So we'll set up, this is a symbol, by the way, for an AC voltage source right here. It's got the little squiggly line in there. Don't pay any attention to the plus. And this would be a device called a capacitor. And that's the symbol for it. And all we're going to do is we're going to come over here and put an ammeter in here. And all we're going to do is we're not going to change the voltage. We're just going to change the current. So let me find the ammeter. It's right, nope. It's right here. Now we have to set this up to measure AC. And then we'll come up here and put a resistor in here. So the resistor, the value of the resistor does not change. But the ohm value of the capacitor changes depending on the frequency. And we're not going to show y'all something to get y'all totally confused. So we got 120 volts. We'll plug this thing on, see what current we got. But this is at what? This is at 60 hertz. Y'all understand that now? So what we got at 60 hertz? 42.8. So let's change this to 120 hertz. Hopefully the simulation works. What did the current do? Should double. But I didn't change this guy. And 120 volts has to be dropped between this guy and that guy. So what happened is this guy, it didn't change values. So how did the current go up? Well, the current had to go up because the capacitor's opposition had to do what? Go down. So let's lower the frequency. So let's go down to, let's see if we can do 0 hertz. Must be greater than 0. Let's do 1 hertz. It don't have to be greater than 0, but notice what happens here. The current almost went to nothing, right? You understand? Well, I didn't change the 1K resistor. All I'm doing is changing the what? The frequency. Now this becomes very interesting. So now we got a device that responds to what? Frequencies. So let's go up to 1,000 hertz. What should happen? The total current in the circuit should go up, right? Because the capacitors drop in less voltage. See that? Isn't that neat? Now what happens when I come over here and put an inductor into my circuit? Let's find the inductor. Here it is right here. It's going to do exactly the opposite, you're right. If I can get it in there. It didn't want to go in. Normally it just goes in there, but I don't have to do this stuff. Normally it'll insert itself in there. Oh, I think I know what's wrong. The power's still on. Normally it turns off when you, okay. So what we have 1,000 hertz. Okay, we'll turn it on. So we got what? 120 milliamps. So let's drop it down to 120 hertz. And the current goes down, right? Y'all see that? Didn't it? It stayed the same. Oh, that's this is a simulation. I don't know why. So 1,000 hertz. Okay, so there's 1,000 hertz. It's 101 milliamps, right? Here's 100 hertz. Current should go up. So now it's 119, right? And I don't know if it'll let me go down to 0 or not. Now you notice it's almost what this guy right here would be conducting. If this guy was here by itself, that would be 120 milliamps. So the lower I go with the frequency, the opposition of the inductor goes down. The higher the frequency, the opposition of the inductor goes up. And the capacitors and inductors are just opposite of each other. Now an inductor is nothing but coils of wire. And that's why the symbol looks like that. So that's the symbol for an inductor. So all your transformers are inductors. It's just they bring the wires real close together and they use something called mutual induction. So anytime we put current through a conductor, we create a magnetic field, right? You understand? And then if a conductor moves through a magnetic field, it generates a voltage. Thank goodness, that's the way most of our power is generated. Number of conductor loops would be number 2. The number of conductor loops. Yeah, and the speed of the motion. This is D. And we call it relative motion, which means you can either move the wire through the field or move the field through the wire. So if your car has an alternator, you don't change that, right? Now the problem is this is the problem we have with automobiles is they're constantly changing what? The speed, yeah. But what we can do is we can change the what? Strength of the field. And that's the way your car regulates. So what happens is if the output of your alternator tries to go up when you step on the gas, your regulator decreases the strength of the magnetic field, which causes the voltage to maintain. And that's what the regulator on your car does. Because you're constantly changing the speed. If that wasn't regulated, you hit the gas and it'd blow out your lights. If you stop at a red light, then your lights wouldn't work. But it has a regulator out there, right? You understand that sits in what? Well, it sits in the output voltage, and it's constantly changing this electromagnet right here. So that's spinning, guys. So what we have these things called slip rings, if y'all seen them. And they're nothing but solid copper rings. And then they got these things called brushes, which are carbon brushes that ride against the slip rings. And then this goes out here, and this is what's spinning around with it. And of course, what usually goes out on your alternator is these brushes. And you go out and buy another $200 alternator, and they send it down to Chancey's down here on 4th Avenue, and he changes the brushes out for a couple bucks. That it might do. There goes James. He had to leave early.
That's done. That's done.
Yeah, he's got to go to Texas, so he told me he had to leave early. So you don't have to know this. You'll learn this in DC. This is the point of, so when we buy capacitors, we buy them with something, we buy them in a unit called farads. And that would be C out here. And then, so to calculate the amount of opposition, which we call capacitor reactance, I don't even need to write this down, guys. It's no learning today, city. We don't really need to know that here. It's just showing you what's going on. So it's 2 pi, which we normally would use 6.28 times the plus L. Frequency times the capacitor, you take the reciprocal of that. And we buy capacitors by C out there. So it's kind of like ohms on resistors. And they're called farads, so you go out. So, I didn't look at it. So when we looked at electronic workbench, I don't remember what the farads on my capacitor was.
That's normally the blows on the dryers.
Huh?
If you got one of those front load dryers, Whirlpool, whatever, maintain it. It's a capacitor on it that always blows. That makes you cold on.
No, that's probably not a capacitor. There's a capacitor on there, but it would surprise me if it was a capacitor. That's what we're going to talk about. Why do we need capacitors? Capacitors act like filters. Filters means you get rid of stuff you don't want and you keep stuff you do want. In the old days, before they came out with something called a phase-lock loop, this is the way we tuned our radios. We got devices that cancel each other out. So inductors and capacitors are exactly opposite of each other. So if you put them suckers in a circuit at the same time, they cancel each other out. But if they're only going to cancel each other out at a certain frequency. We refer to it as the resonant frequency. So that's what you used to do when you were tuning your TV or tuning your car, is you were setting up what we call a tuned circuit. You left the inductor alone and tuned the capacitor, or you left the capacitor alone and tuned the inductor. And once you set up a resonant circuit at a certain frequency, it would let that frequency come through. We still see that on our radios in our car. You don't see it in your TV because they don't give you the frequency of these different channels. All you got is a channel number, right? You understand? But on your car, you still see the frequency of what we call the carrier. So it's in FM, it's in megahertz. You look in your dial, it still says what? Megahertz. AM is going to be in kilohertz. And what you're doing is you're setting up what we call a tuned circuit. So when you dial in that station, you're letting the carrier get through, and then we use these guys to strip the carrier off using filtering, which is pretty good. But there's another thing that goes on that is kind of strange that we'll look at in a second. We'll actually look at these. So this is the formula for inductance. We buy these in things called henries. Now, if you go out and you got a single phase motor, a single phase motor is probably going to have a capacitor on it. We'll talk about later, and it's going to be rated in farads, and it's designed to go along with the inductance of the motor. So it means if you've got if that capacitor goes out on your motor, then you just can't go out and buy any one of them you want. You need to make sure you get the same farads on that motor that it's supposed to have, right? You understand? Because if you don't, it might start, but it might not run correctly. But any coil of wire is an inductor. So when I look at a transformer is nothing but a bunch of coils of wire. So a transformer has a bunch of coils of wire we call the primary. It's got a bunch of coils we call the secondary. They're bonded together with a metal core. And when this guy here adds current, it does that mutual induction, just what I was doing over there, right? But there we're going from a magnetic field between two wires. And I don't have my little homemade transformer up here. These are some capacitors. Now this is what we need to understand right here. But we'll talk about that after y'all take a break. So what does this say?
Phase shift.
For reasons we aren't going to discuss, y'all learned this in AC, is that capacitors and inductors cause phase shifts at the end of the circuit. Now, what we have to understand, any wire that comes close together creates a capacitor. And anytime you have a loop of wire, it creates something called an inductor. these devices called phase shifts in a circuit. Now, what this is right here, if I can get it over here, this is a device called an oscilloscope. Now, oscilloscope shows you what's there. Your meter is going to average everything out. So this is the big problem with a meter, is it don't show you what's there. So I'm using a, if I can get this up here. So this is a sine wave. And what we're doing is we're using this device called a function generator to generate the sine wave. And what I'm doing is these two signals, I've got two signals up here, and they are in phase with each other. It means their positive and their negatives are on, would be on top of each other. Y'all see that? They occur at exactly the same time. Can y'all see that? Okay. What I'm going to do is I'm going to add a capacitor to the circuit. What do you notice now? They're out of phase. So now they're out of, and this is in the same circuit. I mean, these are not two different circuits you're looking at. This is inside the same circuit. In fact, here's the little circuit. If I can get my camera, it's right here. Here's my capacitor, and I got a 1K resistor in there. Now, sometimes this causes us problems, but sometimes we need this feature. And of course, the phase shift, by the way, is going to change with frequency. So the higher they make it the frequency, they're going to start moving back in phase with each other, because this is a capacitor. Oops. See, so now they're a little closer. The lower I make the frequency, the more I will get out of phase. Because as frequency goes up, X of C goes down, right? Or opposition goes down. But you can see if I start lowering the frequency, the phase shift starts getting more. Of course, the opposition of the capacitor is going up, so my voltage drop. So you see that phase shift. Y'all see that? Now, where would we make use of that? Now this is bad, but then it's good. You ever watch Hee-Haw?
Yeah.
This is bad, but then it's good. It's good. At our church, we have a Hee-Haw Sunday every one annually. It's fun, but they do a lot of that.
Okay, you said where would we see?
The problem we have, first of all AC motors act like inductors. So predominantly, the power grid is inductive because all your transformers, all your motors have a bunch of coils of wire in them. Okay, and what this does, this creates if the current and the voltage. By the way, capacitors do no electrical work. They drop a voltage, but they don't do any work. There's no current flow through them. The current flow on a capacitor is in and out of it. So what happens if I've got an ammeter in an AC circuit and I measure current, and then I measure voltage, we learned that power is equal to V times I. Well, the problem is that you're measuring total. You're measuring this out of phase stuff. So what happens is we end up, so the predominant power grid, it tries to lag. So that means the current is trying to lead. And this is an oscilloscope picture that I just showed y'all up here. It's just that one I got was a little better. Delivering power and the current out of phase makes the source deliver more power than actual work being performed. The out of phase power being required for the voltage source is called apparent power. This is given in units called VA or volt amps. So anytime you see something VA, that is apparent power. Real power is in watts. Real power is work. Apparent power is the work that we appear to get. Okay. So there's something called a power factor, and basically it's the true or real power divided by the apparent power. Now perfect would be 1. Because if you got a perf, that means your power and your real power were exactly the same thing. That's what we're shooting for. Okay. Y'all understand that? Now, normally power factors are given in percentage. So Alabama Power requires you to, if you're a big company, now they take care of the power factor at your house. That's why when you pay your power bill, you pay a wattage bill. If you work for a company called like U.S. Steel or something, then if U.S. Steel runs a power factor of greater than 95% or less than 95%, which would be 0.95, then Alabama Power charges them a penalty. Now, a lot of people can't understand that. They're saying, well, U.S. Steel is paying for more work than they're getting. But you got to understand the power grid has to support apparent power, which means all the transformers would have to support apparent power. All the conductors will have to support apparent power. So, and that would cost the power company so much money that it behooves them people to run a 1% power factor, 100% power factor. Now, what they do is they have different ways that they correct for power factor. Remember, capacitors and inductors are just opposite of each other. So I don't know if you ever noticed this, but you're driving down the road and you see these power poles, and every once in a while you'll see one that's got 3 little square boxes on it. Not round square boxes. Those are capacitors. What are they in there for? To correct power factor. That's exactly what they are. The substations have banks of capacitors that they automatically switch in and out depending on the power factor. So they're correcting for most substation actually corrects for the power factor. So this is so if you go out and buy a transformer, transformers are not rated in watts. Transformers will be rated in a current or a voltage. Your industrial transformers are going to be rated in VA. New motors, not the old motors, but new motors have a power factor rating on them. It's not quite the power factor, but what you do is it allows you to calculate what size capacitor you need to put in parallel with your motor to increase the power factor of the motor. But that's going to be on new motor, a nameplate, not on old ones. So now motors have to give their efficiency. They didn't used to have to do that. They have to give the power factor rating of the motor. That's the new stuff that they got to put on motors, and we'll look at that a little more. Did anybody take the ACDC motors class last semester or in T1? Yeah, I think so. No, we only teach it over here. They use the blue trainers. We'll be using the white trainers. The motors class uses the blue trainers. And I just wonder if Hoyt teaches that, because he really needs to teach that, because that's very important, is understanding the difference between true power and apparent power. And Alabama Power's got to deal with that. So that's the biggest problem they have with transmitting AC, is anytime you go through a transformer, it tries to create a phase shift. So what do they have to do? They try to compensate for that, by the way. You can buy capacitors, they call them power factor capacitors, that you can buy for your house if you get them online, but that's kind of like the people who say you can increase the efficiency of your car by 150% if you install this little gadget on there. So the problem is if you overcorrect, it's just as bad as undercorrecting, right? You understand? And the power factor for residential customers are compensated for by Alabama Power. It's just big companies that's got to worry about the power factor. So they had one guy out when I worked out at U.S. Steel, Ed Vining, and that was his job, is to monitor the power bill and the power factor at the company. So if a power source is supplying 100 VA to a circuit that requires 80 watts of work, what is the power factor? Well, it's the true power over the apparent power. So it'd be 0.8 or 80%, which is not good, right? Alabama Power will charge you a penalty for that. Now, the problem we have is that most of the motors we run, we call them induction motors. And what do we need to induce a voltage? Well, we need to have a what? Magnetic field. right? What's the second? Yeah, I gotta have conductor loops. And then we gotta have what?
Speed, motion.
Then we gotta have relative motion. So that means if I had these conductors, so they call it squirrel cage. So this has rings in it. That's the conductors. And what we do is we come up here and we put AC on this. This flies through there. So if this is a north, this is going to generate a south. And what would they do? They would attract each other, right? You understand? Well, if this goes south, this generates a north, they would attract each other. And that's the way a single-phase motor would run. So a single-phase motor would never run. It'd just sit there and hum. So to make a motor run, you've got to have one of your fields has got to do what? It's got to shift. So three-phase, we don't have that problem. So a three-phase motor, the fields are 180 degrees out of phase. So when this one starts dropping down, this one's coming up, and it causes the field to do what? To rotate. So three-phase motors, we have no problem. Like three-phase motors will come up and run, unless you lose one of your phase. And we call that single-phase. And by the way, there's no such thing as two-phase. So if you lose one phase, your motor sees that as single-phase, and the motor, if it wouldn't start, it'd sit there and just do what at you? It would hum, because we got to have the magnetic field on the outside has to rotate. So what we need to do is we come over here and we have another winding over here. And sometimes we use a capacitor. We call these capacitor start motors. And what does the capacitor do? Well, it creates a what? It creates a phase shift. So now that the single phase motor will do what? It'll turn. Now, once something's in motion, it's going to stay in motion. So most of the time, what they'll do is this will be a very cheap wire. It won't be very much, and they'll put what they call a centrifugal switch in here. So when the motor comes up to speed, it'll kick out the start winding. You don't need to start winding except to start the motor. And y'all can hear it click, click. We have another motor that we call a split phase motor. That's an induction motor. And what it uses a lot of inductance out here on the start winding. Now these guys don't have as good starting torque as a capacitor motor, but they're a lot cheaper to make. So your stuff that don't require a lot of starting torque usually uses what we call a split phase motor, but anything that requires a bunch of starting torque is going to use a capacitive motor. And we have some they call capacitive run motors, but actually it's just got another capacitor that they leave in the start winding all the time. And it creates more torque, more run torque for a smaller size.
So what you're saying is you could theoretically, I mean, it wouldn't be efficient, but you could theoretically run a three-phase on single phase. It would just not be.
Well, if it's running, it would run, but it would burn itself up. We call it single phase because the other two motors are going to try to develop their horsepower. So if you got a 30 horsepower motor, it's going to try to develop 30 horsepower. If you lose one of your phases, then the other two windings are going to try to make up the difference, which means they're going to get real hot if you don't have anything in there to sense that. And we'll talk about that later on. We call them overloads. That would sense if you lose one of your phases and the current in the other two phases try to go up, because that burns your motor. Burning the coils up on a motor is a very, very expensive proposition. I mean, you're talking rewinding motors is not expensive. It's not cheap because it's not easy to do. We got some videos we'll show y'all where they show them actually making motors and how they wind up stuff. Well, we use what we call induction motors. So the advantage of induction motors is there's no connection between the rotor and the stationary part because the current is induced into the rotor by this mutual induction that we talked about. So it works kind of like a transformer does. But the problem is to get that motor to turn, the field on the outside has got to shift. Well, single phase motors, it wouldn't shift unless we put something in there that gives us a what? Phase shift. We can either use inductors, those are split phase motors, or we can use capacitors. We call those capacitive motors. Now, capacitive run motors, they have two capacitors on it. One of them is in all the time. If you have a true phase shift all the time, it can create more run torque. It won't create more start torque, but it creates more run torque. So what they do is they're more expensive, but the motors themselves are smaller. So if you're limited to the amount of space you can mount a motor in, then odds are you're going to use a capacitive run motor. If you're not, then odds are you're going to use a capacitive start motor. But the capacitive run motor is actually a capacitive start, capacitive run. You can see these capacitors. A lot of the motors, they'll have big old humps on the outside. Those are what? Those are capacitors. Now, most of your HVA system, they'll have two ground wires that come out, and they use an external capacitor. Now, why they do that is that those things go bad all the time because they're outside. They're outside with all that lightning and stuff like that. So if you got a motor in your HVA system that just sits there and hums at you, then what does it probably mean? It probably means the start capacitor just going out. Instead of going out and putting a new motor in there, then just do what? And I'll show y'all later on how to check these things. These big capacitors you can check with an ohm meter. You can actually watch them charge and discharge. And then some meters have capacitance meters on them, but usually this is a no-go situation. These are the guys that they either work or they don't work. So we can check those with an ohm meter. But this is why we need these capacitors, and this is one reason we need it. So these are where we would deliberately add capacitance to the circuit, or we deliberately add inductance to the circuit so we can create a phase shift to cause the single phase motors to run. To start, right? You understand that? By the way, another way you can tell if it's your start capacitor, if you got access to the shaft and you come up there and you spin it and it runs in whatever direction you spin it in, then that's definitely the start capacitor.
So you can make it start manually.
Yeah, if you manually start it with your hands, and it comes up and runs, but the problem is it'll run in whatever direction you spin it in. So which may or may not be good. Some motors you don't want to run it backwards. That's not true. I had the evaporator motor on my air conditioner go out, and it was pretty expensive, and for the fan, for the evaporator, and a guy had one and put on, but it ran the opposite direction. So my air conditioner run it a long time. Instead of sucking air through it, it blew air out. So sometimes it don't make any difference. Sometimes it does. It would make a big difference in an elevator, wouldn't it? But it didn't. It wasn't near as efficient. Guys, I know this is a pretty good deal we got to get through. I know this usually takes 2 classes. So everybody, conductor terminology. So we have what we call a conductor. Everybody okay with that? So usually when we use the term conductor, we're talking about a inductor that's encapsulated in what? Insulated. And what's the insulator on there for?
Protected in the environment.
Well, yes and no. In conductors, we learn 2 terms. We learn what we call a jacket, and we learn what we call an insulator. The function of the insulator is to keep that push in. That way I can handle the wires, or I can bring wires close together and we don't have contact with it. The function of the jacket is to protect the insulator from the environment. Now, a lot of times the jacket and the insulator are the same thing. But I don't know, anybody ever play around with residential wiring before, Romac? You get them wires, you peel them off, you got that little thin clear coating on those conductors, that's the jacket. And then that thing that goes out on the outside, that white thing on the outside, that is the jacket. That is not in there to protect it from voltage. That's to protect that cable from the environment, period. So technically, the jacket and the insulator can be the same, but a lot of times, especially in cables. So what's a cable? What's a cable? These are groups of conductors, right? Groups of insulated conductors that are contained within a common jacket. So we run into cables all the time. Then we have what we call stranded conductors, which is what we have. Stranded conductors and solid conductors. What advantage do solid conductors have?
You can pull more current, and
Usually stranded can handle just a slightly bit more, but not enough to make any difference. So we don't rate them according to when they're stranded and when they're solid. So when we say a 20 gauge wire, we don't give it as a stranded or a solid. So it really don't make any difference. The ampacity doesn't make any Stranded is more flexible. Solid is easier to terminate. So if you work in house wiring, you just take that old solid strand and wrap it around the screw and tighten it down. If that was stranded, you couldn't do that. Because as soon as you try to tighten that screw down, we call it bird caging, it spread out. And if you lose one strand, you change the gauge of the wire, right? You understand that? So the advantage of stranded is more expensive. You ever see the machines that make stranded wire? It's really, really expensive. They have different ways that they spin them, but stranded wire is more expensive. But it's more what? Flexible. Solid is easier to terminate, which means we can wrap it around a screw and tighten it down. We can twist them together. So house wiring is basically you wrap stuff around screws and tighten it down, or you do what? You twist them together and put it under wire. We can do that with stranded wire.
I was running some wire to my worksheet, my welder. Was it 14? 14
Well, 14 is rated at 15 amps, so it depends on how far you run it, right?
Whatever I said. No, I was saying that I was trying to put a plug out in my worksheet for my welder.
What you ought to do is run 240 out there and then split it up. Yeah. What would be the advantage of running 240 out to each shed? Smaller wire to handle more current, right? You understand that? And then when you get out there, then you split it up and use 14 gauge out at your shed, inside your shed. And if you bury it underground, you need to either put it in conduit or buy underground cable, right? And don't run regular Romax through the air.
No.
Yeah, you see it all the time.
Yeah.
It'll dry rot on you. I mean, they'll run extension cord. No, it's not. It's not. My cousin wanted he had an above ground pool, but he wanted to run everything out there. So it's very expensive, but it's probably the gray conduit is not bad. The underground conduit, the plastic PVC.
That's what I put in.
So these are what we call traces. Y'all, we call these traces or foils. These are on printed circuit boards. It really don't make any difference in this class. We're not going to do this, but we're telling y'all some other stuff y'all might need to know. These are conductors. So they're individual. Sometimes they're color coded, sometimes they're not. These are color coded. This is actually inside a desktop computer. So we can look at the color of the wire and tell what it does. These are cables. So a cable's got to have what? At least 2 conductors. And this outside is what we call the packet. And you'll run into a bunch of cables because cables are, you're running a group of wires at the same time, right? You understand? So instead of having to pull those individual conductors, you run one at a time. Or you run multiple conductors with the same pull. Stranded and solid, stranded and solid. By the way, you gotta be real careful with solid, because if you nick this at all when you strip it, then it's gonna break really easy. This guy, if you nick one of your strands, then you might be okay. It breaks. But there's a chart I can tell you that can tell you the number of strands you're allowed to move on a stranded conductor. But basically, the only advantage of a stranded conductor is what? Flexibility. And sometimes that's what you need. If you ever run house wire in that solid strand 14 gauge, you get us in the 20 gauge solid strand wire, that stuff's not easy to run.
Try doing 3 off.
Huh?
Try doing 3 off.
3/0, that's some good side cable.
I've been 3 off.
Well, splicing, this is the term we use. What splicing, permanent or semi-permanent, joining 2 or more conductors together. Termination is the act of conductors coming to their final destination. So all conductors eventually come to a final destination, right? What's the function of the conductor?
Terminate.
What's the function of the conductor?
No, the function. Carry.
Carry the current between the power source and the load. That's exactly what it does. It's just what your blood vessels do. They don't do any work. power work, well, they just get the blood to the things that do the work. Power cables, conductor cables, this is what we're gonna be using. Some of ours are gonna be signal cables, which we'll talk about later on. I think this is about it. We're finishing up pretty good. So we have power cables, which are intended to carry power. We have signal cables, which are intended to carry what? Signals. This is very important. This has became, within the last few years, originally we had the National Electrical Code. The National Electrical Code, contrary to what a lot of people believe, the National Electrical Code is written to protect the equipment. Y'all understand that? But odds are, if you wire things right, odds are it's going to be safe, right? You understand? But there's nothing in there that says safety. It's all deals with current, how to correctly install stuff. So what they realized, especially Ocean, realized is there was really no standard for worker safety. So the National Fire Protection Association, which puts out the NEC code, by the way, it's the 70 standard. They came out with what they call NAFTA 70E. Y'all heard 70E? 70E is what the employer has to do to protect you. One of the things that this brought about is actually finally giving a rating to meters. So if we look at this red meter right here, this is before categories came out. So this is not rated at a category. But what these categories tell you is they tell you where the intent or where these meters are supposed to be used at. We call them CAT, by the way. So a CAT 1 meter, where can we use CAT 1 meters at? Yeah, electronic work. Now we can always go back, but we can't go up, right? You understand that? So that means a CAT 2 meter would meet the specifications of a CAT 1, but a CAT 1 wouldn't meet the specifications of a CAT 2. Okay, y'all understand that? So CAT 2 is single phase work. So if you worked inside your house, everything you did was in your house, then a CAT 2 meter would be okay. As soon as you do 3 phase, you need to go to a what? CAT 3. We have 3 phase in here, so that means the minimum meter that you got to buy has got to be at least a what? CAT 3. And then we have a CAT 4. CAT 4 is on the distribution side.
The true RMS, is that rated at CAT 4?
Oh, I don't know. Usually they're CAT 3, CAT 4, but they're different voltages. This is a CAT 2, CAT 3 meter. But the CAT 2 is 1,000 volts and the CAT 3 is 600 volts. And we'll talk about those.
Is that why it specifies CAT 1 and CAT 2 instead of saying CAT 2 and 3?
Well, you have different categories of these categories. You have, depending on the maximum voltage that you could measure in that category. So that means the CAT 3, a CAT 2 1000 means I could measure up to 1,000 volts in a CAT 2 source, but I couldn't use it in a CAT 3 source.
Basically, what you're saying is you could measure 1,000 volts in a single phase.
Single phase.
And then
3 phase, it's a CAT 3, it's a CAT 3 600 volt meter. So that means you can safely use this meter. It's guaranteed not to blow up to 600 volts on a CAT 3 source.
Basically.
So a lot of people think, well, the CAT 2 meter is better than the CAT 3 because the CAT 3 is rated at 600 volts and the CAT 2 is rated at 1,000 volts.
Yeah.
But that's 1,000 volts in a CAT 1 and a CAT 2 source. If you had a 1,000 volt CAT 2 meter and that's all it was, you couldn't safely put that into a CAT 3 source.
Yeah.
Now what is protecting you against is most of your problems occur with surges. So like when a lightning strikes or something happens, our power grid's all over the place, right? You understand? Because where the regulators and our generators are a long distance from where I'm at. And there's a lot of things that could happen between point A and point B. So when we talk about 600 volts, that's the maximum you should measure it, but what we're going to do is look at what surge they can handle. What we're saying is that a CAT 4 meter, 600 volt, could actually handle a pulse of what? 8,000 volts. Now, 1,000 volt Cat 3 meter could handle what? I'm sorry, here we go. So it was 1,000 volt Cat 3 meter,
6,000.
okay?
Cat two.
That's cat two. Yeah,
Yeah, but I'm trying to go back to what this meter is. So this meter is a 1,000 volt Cat 3,
Cat two.
I'm sorry, 1,000 volt Cat 2, and it's a 600 volt Cat 3. But you notice the surges are what?
Same.
The same, but this would be in what? 3 phase, this would be in single phase.
Okay.
Cat 2 is a single phase meter. That makes sense. So which one would give you more protection? Well, in a Cat 3 source, this guy right here would give you the most protection, right? And then Cat 4, these are on the distribution side, and so a 600 volt Cat 3 meter, a Cat 4 meter is rated at what?
8,000.
8,000, right? A 600 volt Cat 2, Cat 3 would be 6,000. 600 volt Cat 2 would be 4,000. But they're all rated at 600 volts. So what we're doing is we're looking at the amount of the energy that meter can absorb if it sees a big pulse, right? You understand that? And what the voltage rating is what is the biggest voltage it doesn't mean you can't get into a higher voltage. It said if you got 1,000 volt range and you've got a 600 volt Cat 3 meter, a 600 volt Cat 3 meter, it's protected at 6,000 volts. But only if you don't get above what? 600. Y'all understand that? And that's what those ratings. Okay. So what do we require in this class? A Cat 3, at least 600 volt Cat 3 meter. But most of your meters are going to be, most of your better meters are going to be a Cat 3, Cat 4 meter. The Cat 4 will probably have a lower voltage rating than the Cat 3 rating. Right? And where's this information going to be at? Yeah, it's going to be toward the bottom of the meter. Y'all didn't see what I was looking at. Sometimes they're above the terminals, sometimes they're not. So here's this one, if I can find my camera. So if it focuses in, so there it is right there. So this guy right here is a Cat 2 1,000 volt meter, Cat 3 600 volt meter. Huh? I don't know if it'll focus or not.
It's my glasses.
Yeah, I can't get it.
It's not gonna focus.
Huh?
Use the zoom in function on that software.
Yeah, I don't know if that'd work. Let's see. Usually when we zoom in.
Yeah, there we go.
Just kind of weird.
And I think I can manually focus it too. I think. So normally it's going to be down where we connect our meters. Now you see this. This has no rating. So what does that mean? Well, it don't mean much. It says this meter came out before the rating standard. It don't mean it's not a safe meter, but we don't know. Y'all understand? We don't know what type of surge it would protect me against. Yeah, in your hand. Y'all know what happens when things expand real fast. A lot of people are killed because of these guys right here. And normally it means they got their meter, yeah, they blow up on it. And the problem is if you're in a high voltage circuit and then your meter arcs, we create what we call ozone. Ozone has a very small resistance. Now you end up with an ozone short circuit between the two things. It creates what we call a arc flash. Arc flash creates what we call an arc blast. That arc blast is over around 32,000 degrees. If you get into that thing, you are in trouble. I mean, you are in trouble. A lot of times it deals with people putting their dang test equipment in something that it was not designed to handle.
I was thinking as standalone, it's not going to hurt you. You have a source of power coming through.
Yeah, as long as you're not in something that's got a lot of extreme, but you're looking at, these big industrial companies. If you go to work for industry in the electronic trade or electrician trade, you are going to be dealing with high voltages. Why? Because they got to get that power out to those big old motors. And they're not going to run a wire out there that's got to be a foot in diameter, right? You understand? They're going to step that sucker up. They're going to use like 6,000 volts and make those conductors real small. It really surprises people when you see these little conductors running into these high horsepower motors. But why can it do that? Because it's at such a high voltage. So you get into these big, I think somebody told me US Steel has some motors that run off 6,600 volts.
Yes.
You get into 6,600 volts with the wrong meter and you create a little arc, then you got problems. But as long as you take care of yourself, and that's why now if you get into a voltage like that, you're going to go in with your bomb suit on.
Right.
Yeah, because that's what 70, it's basically a bomb suit.
Yeah.
I mean, it's insulated, it's got padding, you got your helmet on, it's sealed up on the bottom.
Anything else?
Going in.
Volts you had to put on
The whole year.
Yeah, US Steel. Now, 500 volts don't mean it. It's what current is available and how far you're away from the source. But, you know, those guys are right up there against the source on those big old motors. And so, yeah, they get into those. And those bomb suits have saved a bunch of people. Huh?
They had a plan to fix it, and too much trouble put on.
You had to scan the videos.
Yeah, but too much trouble.
I got so I get outside the room, and they go flipping them burgers.
We'll show y'all some arc glass and arc flash stuff. We got a good video on that when we get into safety. Everybody okay? So a multimeter's got to have at least what? 3 functions. What are they?
Oh, yeah.
Okay. Y'all understand that? Can it have more?
Yes.
Yeah.
Yeah. I've never seen one with that. So how do we take voltage measurements? Across. Right? How do we take resistance measurements?
Power.
Yeah.
Yeah.
Across with what?
Power.
So here's some pretty good safety procedures. It says what? If possible, remove power from the circuit when attaching and disconnecting leads. Use alligator clips on the end of your leads if possible. Select the correct unit being measured. That's got a lot of people hurt. We have a problem in DC where people get in there and they'll measure current. And then they want to measure voltage and they forget to do what? Switch over.
Yeah.
And then they blow the fuse in the meter. Well, here that's not going to cause a problem. It blows the fuse in the meter. We had a guy down in Columbia teaching high school kids, and he bought all these beautiful meters. And I said, you better buy a bunch of fuses. So I ain't gonna need any of those. He said, Mom, he said the first time they used them, they blew about 6 of them. And y'all gonna do it. You're gonna blow fuses in your meter. Place the black lead of the meter in the what? Common terminal, the red lead in the meter. Now we don't have it in the circuit yet, right? In the both on terminal, place the lead in parallel or across the device or power source to be measured. Voltage measurements in DC circuits require the black lead. Now this is not exactly true. It don't require the black lead. It's just that on a digital meter, if you hook them in backwards, you're going to get the opposite polarity of what's actually there. Everybody understand that? But it's not going to hurt the meter. Not unless you got a no analog pointer meter.
You don't get the right answer.
Huh?
You don't get the right answer.
Well, you get the right answer. It's just got the wrong sign.
Yeah, well, that's what I'm saying.
But if you've been in the trade long enough that you know what's going on, then most of us don't really pay that much attention. In fact, if you ever see me measure circuits, I'll put my meter in one spot and I'll go on this side of the resistor and then I'll move it over to the other side without ever moving my common lead. Because over here it'd be positive, over here it'd be negative, but it's still the same voltage drop, right? You understand? So a lot of times it makes going through circuits a lot faster. If power is turned off, apply the power, record your reading, if possible, remove power and disconnect the probes. Try not to pull them out of them. In the old meters, the probes would come out pretty easy. On our new probes, on the new probes, the lead that goes into your meter is, you know what I did? I'm close my camera. So the leads that go into the meter, you see people cut these off because this is another one of those things where they cut them off to make it inconvenient. So what they do on your newer meters is, as soon as I find my camera, is the actual leads that go into the meter. The banana plug, the banana plug is actually covered, because this happens all the time, where you actually didn't drop your meter, and you got alligator clips, and it falls out, and the leads pop out of your meter. Well, as soon as that happens, this right here is going to be electrically hot, right? You understand? So don't trim those off, but it makes it a little harder to get the leads in and out. So we place the black lead in the what? Common. We place the red lead in the red. Make sure we put our meter on what?
DC.
Volts. Make sure you select the voltage the type of voltage you're going to measure, because if you put it on DC and put it in an AC circuit, it's going to measure zero. You understand that? If you put it on AC and measure a DC circuit, it's going to measure something, but it won't be the right value. So this is a picture of measuring what?
DC voltage.
Yeah, voltage. This is DC. We okay? Current measurement. Remove power from the circuit. So we make most current measurements with an ammeter, not a clamp-on ammeter, but an ammeter, a true ammeter. We're always going to remove power from the circuit, right? And we're going to place the black lead in the black and the red lead in the red. But what we have to do, now we have to break open the circuit. We have to place the meter in line with the circuit or in series with the circuit, because you got to make the current flow through the meter. Ammeters have almost no resistance at all. So if you put it across something, you got a short. Everybody understand that? Now hopefully it'll blow the fuse in your meter, but it could create a spark, which could be bad, right? Apply power to the circuit, record the reading, remove power, remove the meter reading. Snap-on, in their meter certification, suggests that if you're measuring current, every time you finish measuring current, they recommend that you pull out the red lead. So to measure current, we got to do what? Now, most of your digital multimeters, not your clamp-on meters, you have a different place where you go to measure volts and ohms than where you go to measure amps. So that means you literally got to do what? Now what they recommend you do, if you ever measure amps, when you get through, pull that meter lead out. And then why? Now you got to think about where you put it back in. These guys here, they're trying to make these guys as narrow as they possibly can be. So these clamp-on amp meters are going to have two terminals on them that you measure everything with. So that's not going to be that safety where you literally got to move it to measure amps and move it to measure current. So you got to be careful with these guys, but you can see why they do that, because they're trying to make these what? They're trying to make them as narrow as they possibly can be. Right? So this is the way we have to use an ammeter. Now this is a clamp-on ammeter, which measures, it don't measure current, it measures the strength of a magnetic field. And the strength of the field is proportional to the current that flows through it. But when you look at this scale, the scale for the clamp-on ammeter, if it focuses in, is 40 amps and 400 amps. So if I tried to measure AC current like 15 milliamps, this guy's going to show zero. So this only works in high current situations, right? You understand? So clamp-on ammeter is really nice if you work in industry. especially if you do a lot of motor stuff. Three-phase motor, a lot of times we check to see if we got a balance in the phases and that kind of stuff. In electronics, these guys right here are not going to do any good. I don't know what it does on the amp scale here. It says microamps down here. I don't know how high it goes up, but I don't know if that would work in this class. And I don't know if this is DC or AC. I'd have to look and see on this meter. Measure resistance, right? Basically the same as far as what you do with your meter. But what do you always do to measure resistance? Very first thing says what? Power. If the reading, note, if a reading is recorded, isolated, if a bad reading is recorded, the problem is, if y'all hadn't had DC, you know if something's in parallel with something, it's going to reduce the resistance. Well, the problem is, if you measure it in circuit and it measures good, we assume it's good. If you measure it in a circuit and it measures bad, it could be something else that it's in parallel with, right? That's got the problem. So what we do is we isolate one of the leads on your device. Y'all understand that? And then recheck it. So this is measuring ohms. Are we okay? Okay. So this is a digital multimeter. This is a Craftsman meter. And of course, you can see down at the bottom, it's got the watts. This is a Cat 3 of 1,000 volts.
Cat 3000 and Cat 3600.
I don't think it's Cat 3, 600. This looks like a 3 to me. That's okay. The cat will be, the category rating will be where?
Where will the leads connect?
Down here somewhere. This is an analog meter, still available. You'll probably see this is a Cat 2 meter, 600 volts. Now, analog meters are still used. They're not obsolete, like I heard a guy saying you don't ever see these anymore. When you're dealing with what we call tuned circuits and stuff like that, these become very important. But they're still available. You can still buy them. And then clamp-on amp meters, everybody okay with those now? What's nice about a clamp-on amp meter, once you don't have to remove current because the current is not going through the meter. You do have, normally they only work with AC because it's working off that induction we're talking about. There is an electronic sensor called a Hall effect sensor that can measure the strength of a DC field. But if you got that feature on your clamp-on amp meter, it's going to cost a lot more money to get it so it measures DC current. So this is the clamp-on amp meter. I can't see the category on this. This is a Cat 3, Cat 4 meter. Oops. And then of course you can get those in you can also get those in as an analog meter. These are clamp-ons. They're really nice, but you're going to deal, very few of them go down on very low current scales. They work good in high current applications. They're a lot safer because you don't have to do what?
You don't have to break.
Have to break a circuit. By the way, only put one wire through that at a time. If you put multiple wires, the magnetic fields are going to cancel each other out. Y'all understand that? By the way, there is a trick. What determines how much voltage we induce into a conductor? I mean, I'm listening. What determines it? Strength of the field. What's the second thing? The number of windings. So if you got enough slack on these guys, by the way, you can loop. So if you come over here and loop it twice, then your meter's going to measure twice what's there. If you loop it 3 times, your meter will measure 3 times what's there. So all you have to do is a little math, and you can make these guys measure a lower current. If you got enough slack in your wire just by doing what? Looping the wire. That's a trick I learned a long time ago from a friend of mine. I said, man, we can't measure that. He said, well, just loop the wire, Rich. And every time you loop it, if you got enough slack, you're adding more coils to the wire. The magnetic fields combine, and your meter can measure lower current.
Explain that a little bit more. Just tell, you're looping, the wire you're measured.
Yeah.
You loop it.
Yeah, you loop it around here. So what you do, I can't.
I think I figured.
Yeah, so what we would do is, normally we would come in here and measure it like this, right? So we'd take our clamp on that meter, we'd open it up, we'll put it across the wire, and we'd measure this. Well, if I come over here and did this,
Just run it through again.
just run, if I got enough,
Yeah.
now my meter would measure twice what's there. So if it measured 1 amp, it's actually seeing what? I mean, if it measured 2 amps, it would actually be 1 amp. Well, it's just divided by the number of loops. So if you looped it through 3 times, then you just divide your reading by 3, right? You know, that makes sense? Yeah, just divide it by the number of loops, because every time you put a loop, then those magnetic fields are going to combine inside that winding, and you just divide it by the number. And that, a lot of times that'll allow you to use a clamp on ammeter in applications that are below what you're actually measuring. Of course, I couldn't measure this, I couldn't use this in any circuit that we deal with here, but. Our motor is, we'll look at it when we finally hook our motor up. We got I think ours is a 1/2 horsepower motor, and we'll use a clamp on that meter on that. I know we skipped over a break, guys, but we're gonna let you go. So there's assignment 3. What is that? Assignment 3 is to complete a basic electricity quiz. Where's that at? Where's that board? Now, according to the calendar, it's not due until next Friday. But the problem is that normally we like to give these quizzes before the test. The test is going to be next what? Thursday. So it would probably help you out a lot if you go ahead and do what? Do the quiz. The quizzes you can take twice. No more than twice, because after that you're memorizing answers and not learning answers. I'll record it. Y'all just won't be, if you need to ask me any questions, then yeah.
In German.
In German.
No texting, no, just email.
Yeah, next Thursday.
It's right. No texting or calling.
Yeah, but remember we had one class, you missed one class, and that's going to be on test 2, but they're recorded. I was able to go ahead and post that up on Blackboard. And then week after next, the classes are going to be online, right? Y'all understand that?
From 9 to 1. The last week was my birthday.
Because I'm going to be in Germany. I mean, Nancy's going to Germany. What'd you say?
Can you speak German?
I say October. Just what I learned from Hogan Searoad. So here it is, right in, I mean, course content, right? You understand? And this is what? Basic. Then this says what? Topic quiz. Are you okay? And like I said, it's not due until next Friday, but the test is predominantly going to be with this. Hopefully, try to bring your lab books in next class if you need to get them, because we'll be doing what we're going to do. The lab we're going to do is pretty simple. We're going to be inventorying the trainers and make sure everybody's got everything they need and move them back where they're supposed to be. So what happens, we have a tendency for things to float around. So, we're not going to do everything in there, but this is predominantly a lab. This is the longest we will lecture in this whole thing. Normally what we do is we'll be lecture, start a class, and lab to end the class. Any test day will be in lab before the test and take the test at the end. So this is predominantly a lab class. It's just that we got to get this out of the way because we get people in here that's had nothing but intro, and we're dealing with AC. They haven't had parallels. We have to give a little bit on parallels. So predominantly this is going to be a lab class. Now, but due to me being out of country, we're going to do this in a little different. Y'all going to be in a lot of lectures to start off with, and you're going to be in a lot of lab to do what? At the end, yeah. So we'll make up the lab.
So we already took ACE or took DC, so we should be pretty much caught up with the test going on.
Yeah, plus a little bit on AC too. You know, we need to understand just basic AC, not in depth. So you need to know cycles. You need to know what frequency is. You need to know, basically what an inductor does and what does an inductor do. It varies with frequency, right? But the big thing that we need to understand is that it creates these phase shifts, which gives us the ability to have a single phase motor. And then later on, when we get into how do we reverse a single phase motor? Well, if you don't understand phase shifts and start windings and stuff like that, it's not going to do you any good to know how to reverse a motor. And that's one of the big things we'll do, of course. Because this is called what? What's the name of the class? Motor control.
All that same stuff, right? I took the AC/DC.
Yeah, I know, but the problem is that you got to understand this class only has a prerequisite of intro to engineering. So some of y'all have an advantage, some of y'all don't. Right?
Yeah, I already know which one I am.
Huh?
I don't even have a clue.
You got like, you got like email teaching and safety, what you want to hear, safety.
Yeah, that's something you got to go back. You hadn't actually had a safety lecture yet, doesn't So you did send me email? Did I send you back?
No, I ain't seen.
Okay, that's fine. They're not doing this week yet. But that's what I'll do. When you send me the email, I'll send you back.
I took AC in this class when it's all.